All right, y'all. So, like I said, 6C deals with what we call the normal distribution. All right, y'all. So, I'll begin by defining this. So, the normal distribution is a symmetric bell-shaped distribution with a single peak. So, its peak corresponds to the mean, median, and mode of the distribution. All right. And its variation is characterized by the standard deviation of the distribution. Okay, and I'll pull up an example sort of showing you what we're talking about. So let me pull up my PowerPoint. All right, y'all, so this is an example of showing you two distributions. One is going to be what we call normal distribution because it has that bell-shaped curve. And the other one is just a distribution and it is not normal. So A down here, the left side, is a famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846. So notice on the bottom it says the chest circumference of Scottish militiamen. That's the scale on the bottom, going from around 33 up to around 47. And then the frequency on the left side, the vertical, that's how many men had each of the sizes. Okay. Now the figure on the right, that distribution of the population densities of the 50 states. So notice they got on the bottom scale, horizontal is your population density, and then your frequency is on your vertical scale. So notice it is really heavy toward the left side, and then it just sort of falls off as it heads to the right side on that one. So remember, I'm going to show you the solutions, but remember, A looks more bell-shaped to us, okay? All right, so notice their solution. The distribution of the chest sizes in the first figure A is nearly symmetric with a mean between 39 and 40 inches, and in values far from the mean or less common. And that's giving it that bell shape of a normal distribution. The second one shows that most states have a low population density, but a few had much higher densities. So this fact makes the distribution right skewed because it sort of tails off towards the right there, okay? So that would be what we consider not a normal distribution. All right, y'all. So back to the page, and I'm going to give you what we call conditions for a normal distribution. All right, so we got four criteria um, for a normal distribution. First criteria, most of the data values are going to be clustered near the mean or the middle. So most data values are clustered near the mean, giving the distribution a well-defined single peak. Okay, like with the militiamen, most of that data was clustered near the middle. That was what was giving it that big peak for that bell shape, okay? All right, y'all, the second criteria would be that the data values are spread evenly around the mean and y'all remember when I say mean, I'm talking about the average. So data values are spread evenly around the mean, making the distribution symmetric. So I have pretty much just as many values below the mean as I do above the mean. And that's giving it that shape as it heads out. All right, y'all, the third criteria. Larger deviations from the mean are increasingly rare. So what we're saying, the further I get away from that average, these further I go, the values are less common. So that's what's causing it to sort of taper out and look like little tails. So they're increasingly rare, producing the tapering tails of the distribution. So the further I get from my average or my mean, the values are going to be less and less likely to happen, and therefore it's tapering off. All right, y'all, the last criteria, individual data values result from a combination of many different factors. All right, y'all, so let me get PowerPoint ready, and we'll look at some more examples. All right, so this example, is it a normal distribution? So which of the following variables would you expect to have a normal or nearly normal distribution? Scores on a very easy test, or the foot length of a random sample of adult women? All right, so think about it. If it's a very easy test, more people are going to score toward the higher end, which would seem to make that a little bit skewed toward the other direction. You're not going to have as many lower scores as you would if it was a normal test. And then let's see, y'all are saying B on that one. Let's look, the foot length of a random sample of adult women. Yeah, I would probably think that'd be the one too, Jada, because you're going to have that average and you'll have a few of them probably be a little lower and then a few of them be a little bit higher. And so their solutions, y'all, for A, they're saying the tests have a maximum score of 100%. That limits the size of the data values. If a test is very easy, the mean will be high and many scores will be near the maximum. So the few lower scores can be spread out well below the mean. And then on the foot length of a random sample of adult women, let me go to choice B here. All right, they're just saying that foot length is a human trait determined by many genetic and environmental factors. Women's feet to cluster near a mean and become less common further from the mean in both directions. So we would expect it to have the bell shape of a normal distribution. All right, good job, y'all. So B was definitely it. All right, y'all, let me get my camera up. All right, y'all. So let me show you one more picture and then I'll give you some info on this. All right, so you're looking at a picture of a normal distribution. Now, on the bottom, let me explain what these mean. So you see the mean is the middle on that horizontal scale on the bottom. To the right, that is plus sigma. That means that is one standard deviation. Plus 2 sigma is 2 standard deviations. And then toward the end is plus 3 sigma, which is 3 standard deviations. So what they're showing you, and then to the left would be a standard deviation less, 2 standard deviations less, and 3 standard deviations left. So the 68, 95, 99.7 rule for a normal distribution means that 68% of your data points will lie within 1 standard deviation in either direction from the mean. 95% of your data points will lie within 2 standard deviations of the mean. Okay, 2 to the right or 2 to the left. 95%. And y'all, 3 standard deviations from the mean, you have almost 99.7% of your data will be within 3 standard deviations. So y'all, let me write that out in words. So we call this the 68, because remember, 68% of the data will be within 1 standard deviation. 95, because 95% will be within 2 standard deviations. And then 99.7, because that is the percent that would be within 3 standard deviations. So this is the 68, 95, 99.7 rule for a normal distribution. All right, so like we said, about 68%, or basically 2/3, of the data points fall within 1 standard deviation of the mean. And y'all remember, we found standard deviation last week. So the standard deviation is the average of how far the data points were from that mean, okay? All right, about 95% of the data points fall within 2 standard deviations of the mean. All right, y'all, then the third one, the 99.7. About 99.7% of data points fall within 3 standard deviations of the mean. I mean, that's pretty much getting close to 100%, okay? All right, y'all, so we're going to use this data we got and look at this homework and see what we think about these questions they're going to ask us. So it's a pretty short section. All right, we just want to see if these things make sense or not. So the heights of male basketball players at a local college are normally distributed with a mean of 6.3 inches and a standard deviation of 3 inches. So y'all basketball players usually definitely over 6 feet tall, right? And then that standard deviation is not what we would say was very far off. So 3 inches sounds like a decent standard deviation on the height of basketball players with a mean of 6'3". So what the standard deviation means is 68% of them would be between 6 feet 0 and 6 feet 6 inches. Right, that'd be one standard deviation. 95% of them would that be around 5'9" up to 6'9". So you got 95% of your players would be between them heights, and then 99% would be 3 standard deviations from the mean. So y'all, that definitely should make sense. So we would check that and then check our answer. So y'all tell me, does this one make sense or does not make sense? So this one's on y'all. So the weights of babies born at Belmont Hospital are normally distributed with a mean of 6.8 pounds. So the average of all the babies came up to 6.8 pounds with a standard deviation of 7 pounds. So y'all, make sense or does not make sense? And y'all, I'll tell you what I'd be looking at on this. They're saying the standard deviation is 7 pounds. Well, the average they got was only 6.8. So how could a standard deviation be higher than the mean? So y'all should definitely say on that one that that just does not make sense. All right, we want to see if this one makes sense or does not. Jack is in the 50th percentile for height, so he is of median height. Well, median means the middle, and if you're in the 50th percentile, that means 50% are going to be less than you. So that's pretty much the middle. So both of them definitely make sense because they're basically saying the same thing. So we want one that says it makes sense. Um, so this one's saying it makes sense. 50th percentile by definition is the mean height. No, no, no. It ain't the mean, it's the median. So we would say it makes sense because the percentile means that 50% of heights are less than or equal to Jack's. And the median is the middle value. So they're basically saying they're the same like I said. So you want the one that relates the percentile with the median, okay? The middle. Well, y'all think our internets are running low tonight. All right, y'all. So let's think on this one. I'm going to make these a little bigger for you. This is three different distributions. They want us to identify the two distributions that are normal. And then of the two normal distributions, which one has a larger variation? Well, y'all, the two bell-shaped ones look like B and C. See how B is a nice little symmetric bell-shaped curve? And then C is a nice symmetric bell-shaped curve. A would be what you call right skewed because it's sort of tailing off toward the right only. So the two would be B and C. And if you notice, if you took B and C and folded them over onto each other, that right half would fall right on that left half, okay? So you want to go with B and C. Now, which has a larger variation? Well, y'all, B would have a larger variation because it's got more values that are spread out. On C, that's not as much variation because all the values are sort of clustering around that middle, okay? So B would have a larger standard deviation. All right, so this one, state with an explanation whether you would expect the following data sets to be normally distributed. The weights of 200 new pickup trucks of the same make and model. Well, I would expect that to be normally distributed. You're going to have your average, but a few of them might be less, and a few of them could be a little higher, and that could be from manufacturing or something like that. So we would expect it to be normally distributed. But remember, that does not mean they're all the same weight and same size. Will weigh the same because of manufacturing defects. So what about B? Since the trucks are all the same, most of the trucks will weigh the same. True. And then some may weigh more or less due to manufacturing defects, making it normally distributed. Hey, y'all, if they're all the same weight, then you won't have no variation at all. Okay, you just have a single line there. So we're looking for the bell-shaped curves, okay? All right, y'all, so let me show you what we mean by this. The scores on a psychology exam were normally distributed. So let me write this down. With a mean of 64 and a standard deviation of 7. So they're saying a failing grade on the exam was anything two or more standard deviations below the mean. So they want to know what was the cutoff for a failing score, and then what percentage of the students failed. Okay, so let me go to the page. So we want to know the cutoff for the failing score, and then approximately what percentage of them failed. All right, y'all. So here we go. our mean is 64, standard deviation is 7. So they're saying 2 or more standard deviations below the mean was a failing score. So what we would do is take 64 minus 2 standard deviations. Well, the standard deviations were 7. So we would figure out what this gives us for our minimum scores to be passing. So y'all, 2 times 7 is 14. 64 minus 14 gives us 50. Now, let me bring my chart back up here. So we know it's going to be 50 is the minimum score. Now remember, we're 2 standard deviations lower, so we're right here. So 95% of the data is within these 2 standard deviations. So y'all, what's left is the other 5%. But you got to divide that 5% on each side. So this little part would be 2.5%. This little part would be 2.5%. Okay, because 95% will be in between 2 standard deviations. So what's left is that 5%, and I divided that by 2 to get the 2 ends. So let's go look at what they're wanting on the homework. All right, so first of all, the cutoff for a failing score was 50. Because y'all, like we said, 50 was 2 standard deviations from the mean. Now they're wanting us to round 1 decimal place, so that would be 2.5. Because remember, if 95% are within 2 standard deviations, you only had 5%, so each end gets 2.5 of that, okay? All right, also let me see what they're saying here. The length of pregnancy terms for a particular species of mammal are nearly normally distributed about a mean pregnancy length with a standard deviation of 19 days. About what percentage of births would be expected to occur within 38 days of the mean pregnancy length? Each standard deviation is 19 days. 38 divided by 19 gives us 2 standard deviations. So, back on our chart, so 1 standard deviation to this direction, to that direction. And if you notice, we said a while ago that 95% of our data would be within 2 standard deviations of our mean. So that's going back to that 68-95 rule. So we're going to expect 95% of births will occur within 38 days of the mean pregnancy length. Okay? Now, that means 68% of them would be within 19 days, okay? And then further out, 3 standard deviations would have been 99.7. So you're just using that bell curve data for that one, okay? All right, look at this one. Suppose you read that the average height of a class of 37 eighth graders is 53 inches with a standard deviation of 49 inches. Y'all, is that likely? Well, think about it. Your average height is 53 inches in the middle. One standard deviation of 49. Well, from that, you're getting 53 minus 49 would give you 4 inches at one standard deviation. And then add that, that's like 102. So that means that 68% of my eighth graders would be between 4 inches and 102 inches. Yo, there's no way that's happening. So it is very unlikely. And it says because they're not usually approximated by the normal distribution, or this is not likely. Um, would imply that 5%, so that means three standard deviations differ from the mean by more than 98. I mean, there's no way, right? If your average is 53, you can't be further from that average if it's going more than one or two standard deviations. It's sort of would be impossible, okay? Yeah, because you can't have a standard deviation of 98 if your average is only 53, okay? So that's what you're looking at on those. And then check your answer. So y'all, that's basically what you're doing on that homework right there, okay? Um, you're sort of going by the bell curve and using the percentages for one standard deviation, two standard deviations, three standard deviations. All right, so any questions on that? Y'all, pretty short day today.